match between a number of words in a list item, and number of stop words in a list item, seed words in separate list item. Dictionary matches, obviously, regular expression matches also can count. So, I'd like to just explain the one list extraction flow that we have been trying to play with. So let's say I have no data on, I have absolutely no training data on the projects that different people in a university are associated with. And I would like to extract information, who is associated with which project, or I would be interested to know students that have collaborated on projects in the past. So without the training data and without understanding the domain, how do I go about? So what we found to be very effective is some keyword and seed list queries, and these queries could be as simple as student project. It could be as simple as that, or just projects. We could also look at type queries, but these type queries could work off named entity types, very basic named entity types that we've been discussing previously. So these seed queries could be keyword queries. They could also be unordered or ordered formatted queries on very simple top level types that we have discussed so far, for which extraction rules could be built. So far we have experimented only with keyword queries, and what you can get as from those keyword queries, some search results. You could do some re-ranking on those. And what is the idea behind re-ranking? We want to find from those seed queries instances of certain types. So the re-ranking has a particular purpose, and this re-ranking, makes heavy use of visual and lexical features that were mentioned earlier. And these search results can go to the user back for relevance judgment. So what we are doing in this process is actually creating some training data. So do these list pages, do these tables actually contain instances of the types that you are looking for? If they do, the domain expert could flag them as relevant. This could help in retraining the model. The model that we retrain is a rank SVM model. So rank SVM basically learns to rank instances based on certain features, and the training input for rank SVM is a rank list of documents. So it's not just about being a list or result being relevant or not relevant. It's about certain results being more preferred than certain other results. So we can have this model retraining to actually get the seed list of potential candidate entities, and then what we do in the next phase is use some of the technology of finding these patterns, first order patterns within each page to extract seed instances for training data. So this whole process we find can help us not only obtain training data but also learn patterns, the patterns that get extracted here, the rules and DOM based patterns. So here's a simple list extraction system. So let's say I have this ontology sitting on the left, and I can enter a seed list here. Let's say I know that these are 3 people who are professors or who are researchers or who have been students in this university. I just need some seed examples. So this could serve as a base query. Your query could also be a context query, and what you get in response is based on the visual features, a rank list of potential pages which potentially could contribute to your training data. And your relevance judgment is factored in the next time these pages are ranked, and what you get eventually is a training data that keeps growing with every iteration on this corpus. So we trained the model on a corpus of over 400,000 documents from 3 universities, and we got about 50,000 ranking constraints. So it was tested on training corpus, and the test corpus from a different bunch of universities, 300,000 documents. So these are some numbers we got. We've reported map and DCG. Our baseline system is just using a simple indexing engine like Lucene. When we use the lexical features or the visual features, we get improvement, and when we combine all of them, we get the maximum improvement. And in each of these cases, the training, in each of the last 3 cases, the model is trained, the weights for those features are learned using rank SVM. And we also looked at how does it compare with what could be achieved in the best case. So we had some people write very painfully some extraction rules from those pages, which yielded very high precision and recall. The AQL is the language that was adopted for writing those manual rules. And we realized that our approach of extracting candidate pages, bootstrapping and learning and acquiring trading data to obtain DOM and lexical based patterns for extraction, actually our accuracy was in most cases either better or comparable with very meticulously created manual rule base. So that was definitely very interesting, and we are able to keep, this has helped us keep growing the information extraction database. So these are some observations. A combination of visual and lexical features is indeed capable of identifying list documents from a corpus with high precision, and this we can do for a fairly large type system as specified by this academic ontology. And nodes that have well-defined signature like email and course ID, we get 100% accuracy. We also looked at conference and many other close to the evaluation was on a close to 100 annotation types. So others like department name, events and research lab, they also achieve high precision. So the precision of the main bottleneck is the presence of non-list elements like list headers, etc. So list headers is a challenge. So that seems to introduce a lot of noise. We also applied this kind of technique for identifying interesting patterns which are not really HTML patterns, but they are textual patterns from call records. So imagine you have a huge data, you have a huge repository of chat transcripts or call records, perhaps from one of the call centers, and you want to identify calls as success or failure. You want to identify interesting events in those call records, and these call records, these patterns are can be horizontal in the sense they could be within each turn. There could be patterns within a turn, or there could be patterns across turns. Across people speaking to each other, and simple ideas like finding frequent patterns which are specific to classes can help characterize successful and failed calls very effectively. So this can help us capture the voice of customer. This was a database from a call center. So you could have horizontal patterns. For example, canonical question and answer times determined by clustering questions and answers using non-consecutive patterns. So this is an example of horizontal pattern. Or you could have vertical patterns of a particular kind of question resulting in a particular kind of response. So the last part of the talk, I'll briefly talk about entity disambiguation, which could be thought of as entity extraction, but with respect to a fairly large knowledge base. Most of the work I'll be presenting have been using Wikipedia as a knowledge base. So there's going to be some overlap between what I'm going to present and what you heard the morning session day before yesterday. But I'll be focusing more on a specific class of techniques that exploit collective information. So let me introduce some terminology. So assume you have this text document, and I'll just read out some parts of it. Manche is a French department in Normandy named after La Manche, which which is the French name for the channel, English channel. Manche is one of I think some text missing. So the idea is I want to identify spots here and connect them to a database such as Wikipedia, which has millions of I would say entity types. So the entity types could be thought of as abstract as person names, or could be thought of as Michael Jordan, a statistician. So by entity types we really mean nodes in the reference the reference encyclopedia. So these are candidate entities, or you can think of them as types, and what we have in the text are spots. The challenge is to associate spots to these entities. Now there are several interesting possibilities. One is you could have some of these spots not associated with any of the nodes in the reference knowledge base. So for example, I think this is the case of album. So there's some album. So so there's some mention of album behind somehow. I think sorry, this is sleeve. This is sleeve. So the sleeve. So it turns out that this word sleeve has no corresponding entity in Wikipedia. So you can refer to this phenomenon as a no attachment phenomenon. So you don't want to attach this to anything in the reference corpus. You can have other cases where you have multiple attachments, and these multiple attachments arise because of either incomplete context or nearly synonymous meanings. So here is an example: D-Day invasion of Normandy. Now this D-Day invasion it could be a military term, and this invasion of Normandy, if you look at the Wikipedia page, as far as I remember, it talks about the entire event. Whereas D-Day is something that is it's a military term that has evolved thereafter. Operation Overlord is one of the days. So our evaluators found that given the context, limited context, all these entities are relevant. So these are additional problems that you get with a large knowledge base. There is either genuine ambiguity because of lack of context, or there is a case for multiple attachments being all relevant even with the complete context being provided, and the third case is of no attachment. So there's been a lot of work in this area which you might have covered, which might have been covered in one of the earlier talks. Now some of the interesting things that could be of help in this kind of disambiguation, some of the interesting signals would be the context. So the fact that French department occurs in the context of Normandy might help you disambiguate each of them more accurately. So it is the local context as well as the labels, the correct labels of mentions in the context. So there are two kinds of signals which are lexical type, which are words in the context, how they overlap with the definitions of those entities, and related entities occurring together, which is typically referred to as collective signal. So entity disambiguation has received a lot of attention, and most of it has been around Wikipedia. So Semtag and Seeker probably is the only piece of work, the oldest piece of work which didn't refer to Wikipedia, but this was around a very large set of nodes that was developed at IBM Research Labs. This was in 2003. But following that, there have been many other systems like Wikify, Wikipedia Miner, a very simple system called QKZen, NIDA more recently, which have all exploited these two kinds of signals. Signals in the local text and collective disambiguation. So we have studied this problem over the last 4 years or so, and ours was the first piece of work where we actually formulated an optimization problem for solving the problem of disambiguation in a collective sense. So I'll briefly allude to that. And we also extend the idea of collective disambiguation to handle the no attachment problem and multiple attachments more seamlessly. So this is a typical process diagram. So given a collection, in this case Wikipedia, you would create something like a trie data structure, and that trie will feed into a process called spotter. The spotter would find candidate entities, and for each of the candidate entities you would find signals in the document. These signals come from the document as well as from the reference knowledge base. So this part is fairly common, and what happens in the next part is these features are consumed into a model which will decide which is the entity most relevant. So we present two approaches for collective disambiguation, which make use of these features and ensure that related entities come up as the right kind of entities for the document. So let's consider this example. France to host meeting of Afghanistan's neighbors, foreign in Paris, France has invited Pakistan and Iran. So this is an unstructured piece of text. Now what we do next is spotting. So we have found potential spots, which is a spot is an occurrence of text that can be potentially linked to the Wikipedia page. So what you get is a list of all candidate spots in the web page. So we denote that by S0. And then you have possible attachments for a spot. We denote that by gamma S, the candidate entity labels for spot S. And you have a union, you can consider the union of all candidate labels for the page as a set space of entities that is of relevance for this particular problem. So what does this entity disambiguation entail? Again, illustrating with this example. So jaguar could mean, in this text, jaguar could mean jaguar the car or jaguar the animal, and this is what disambiguation takes care of. So at every spot in the document, you have a vector of potential labels, and this vector of potential labels has its own set of compatibilities with the background knowledge. These compatibilities could be computed using overlap with the Wikipedia definition. You could get this by looking at the overlap with the in-link anchor text, anchor text coming from those in-links. So there are close to 7 or 8 kind of signals that you could obtain to identify the relevance of a particular entity to this document. Very interestingly, it is found that one of the most powerful signals is simply the prior probability of that entity. So if there are very few documents which refer to a particular, let's take the example of kernel. So kernel could mean a machine learning kernel, it could mean a software kernel, but perhaps there are there's an obscure meaning of kernel in some other domain. And it turns out that simply using the frequency of kernel, the frequency with which kernel gets associated with one or more of these classes, you could actually do very well in disambiguating. Okay. So obviously that forms a baseline. You need to do better than just the prior frequency. And then, so this is a signal that you get from the reference collection, reference dictionary or directory, sorry. But the other thing you can also get is compatibility, the mutual compatibility of these different candidate labels. So how compatible is this gamma to say a gamma S prime? How related is kernel as a machine learning kernel to convexity, or how similar is a machine learning kernel as an entity to something like a feature, as a feature in machine learning. So this can help collective disambiguation, and this interlabel topical coherence again comes from Wikipedia's graph structure, in-link, out-link similarity between entity pages. People have been trying to make use of the Wikipedia category structure to find similarity. but that's been very disappointing because of very, as I mentioned earlier, there have been very trivial cycles in the Wikipedia category structure. So we, more or less, these are the kinds of features that almost all existing approaches in literature have looked at. And this relatedness information from entity catalog is perhaps one of the most useful feature, which measures the similarity between two entities in terms of their mutual compatibility. So Milne proposed this, it's like this is also called the normalized Google distance. And this turns out to be fairly powerful signal. So we've looked at two different approaches to model this collective information. One is by considering each of these spots as a node in a Markov random field, and considering the potential labels with each spot as the labels for that node. Okay. So this was work in 2009, and what we found is that we can actually pose a nice optimization problem. However, that optimization problem is NP hard, and we resort to heuristics for solving it. But more recently, we realized that, well, there's a different way of formulating this optimization problem, which can actually not only give you optimal solutions in linear time, but also can help you handle the no attachment problem and the multiple attachment problem very naturally. And the solution we found is treat each of the entities as a node in a Markov random field. A Markov random field is basically a graph where nodes correspond to random variables. So just by having a different formulation of the problem, a different probabilistic modeling of the problem, we gain several advantages without actually compromising on accuracy. So what we did earlier, we posed entity disambiguation as inference problem, used integer linear program because we got an NP hard problem, but we were able to solve it exactly in reasonable time. But we were only able to learn the node features. We really couldn't do collective learning. We couldn't do any kind of reasonable learning on the edge features. But with a different kind of modeling, we were able to solve the problem in polynomial time. And we also were able to naturally handle no attachment and multiple attachment. And it's as simple as this. If every node in your graphical model, Markov random field, can assume just values 0 and 1, so it is possible that multiple nodes which are associated with the same spot get a label of 1, which will mean that there could be multiple entities associated with a spot. And it could also happen that there are no entities that get associated with a spot, in which case the no attachment problem gets naturally handled. And because our training is, we get polynomial time training, even learning becomes feasible. So, and we experimented on several data sets. Some data sets which required were publicly available, some data sets which we had to curate and complete the annotations. So I just want to present some interesting numbers. So we find that we again create a system like I presented before, which can continuously evolve not only the model for annotation but also the training data. So what we find is with this data curation, where you have even a simple model like logistic regression, which doesn't do collective annotation, with feedback it can actually improve. The data curation, the accuracy of the model can keep improving. And we also find that not only can a simple logistic regression model improve, but even our collective model for collective disambiguation, which can be trained after every few epochs, can yield improvement in accuracy. In fact, the improvement in accuracy here is more significant. So we find some very quick ways of bootstrapping and creating the training data and improving the model. That's basically the take-home message. And our accuracies, in fact, are better than most of the systems that are reported. And we find that amongst all the features that we were discussing, the the biggest contribution was from outlink and inlink features between web pages, between Wikipedia pages. And as expected, the category feature was disappointing because of the obvious reasons I mentioned earlier. We also looked at other features like frequency, etc. So for the first time that some work has tried to evaluate the impact of different edge features, because so far there was no learning mechanism for the edge features. We are also able to incorporate some user-defined constraints. So it might happen that a user doesn't want more than 5 entities on a particular page. I mean, he believes that there should not be more than 5 entities on a particular page. Or he might believe that at max there should be 2 entities for a particular spot. It doesn't make sense to show up 20 entities for a particular spot. So these constraints can be very intuitively fed into the inference algorithm, and actually the user can instantly see results as per, as desired by him. Some of these constraints might be handy. For example, if you want to index the collection, you probably don't want too many entities coming up. And so we find that, well, you can do precision recall trade-off by changing these constraints. Yeah, and results are actually much better than all existing systems that are reported. So there are some a lot of challenges in this area, the data curation. I mean, it's easier said than done because it's often confusing whether an entity that is shown up as relevant to a particular mention should be chosen or not. So, for example, if you have a ground mention lifestyle, and lifestyle as it occurs in Wikipedia is a candidate entity, you might predict it to be not no attachment, right? So why would this be a challenge? This challenge because the entity called lifestyle in Wikipedia is actually a disambiguation page. So is it fair to associate that with lifestyle? No. But what we often find is some of the ground truth annotators identify this lifestyle with a disambiguation page called lifestyle, whereas the system predicts no attachment, which doesn't seem to be wrong. So that doesn't necessarily show that the disambiguator system has outsmarted the human annotator. We are just trying to highlight that, well, there are challenges, there are a lot of ambiguities, and therefore even data that has been reported as ground truth data in this area, to me is with some footnotes. So basically, we need to question what ground truth really means. So here is another example. Ground mention could be synthesis, and what you identify is this entity called synthesis in Wikipedia. The predicted entity is chemical synthesis, and now again it turns out that synthesis is a disambiguation page, whereas chemical synthesis seems to be more relevant, though the document doesn't seem to be talking about chemical synthesis only. There are 2 mentions of synthesis. One is chemical synthesis, the other is not a chemical synthesis. So there's also a problem with our approach, that we assume that every document will have only one meaning of a mention. So if it's chemical synthesis in one place, it's going to be the same elsewhere. And then there's the third example of harsh reality. So the ground entity, what the manual annotator decided was that it should not be attached to anything. There should be no attachment, because the spot was harsh reality. But it isn't really wrong to associate reality with reality in Wikipedia. So the phrase that he looked at was he or she looked at was harsh reality. So here's a list of, just to conclude, a ground mention like God has a ground entity God as a male deity, but the context, what the system gives is God as a person, not as a deity, but as a concept. This is what you get from the system. Now it's again arguable whether this should be treated as right or wrong. So somehow I haven't seen anyone analyzing and understanding this the process of entity disambiguation itself, Now this is specifically important to us given that Google is going to release a large corpus of documents annotated with Wikipedia. So it will be interesting to see whether these problems have been addressed with some specific set of assumptions. What is really ground truth will be interesting to understand from their release. Last small piece of work I wanted to allude to is, so we talked about finding these node potentials which measure the compatibility of a node with an entity in Wikipedia. So in this case, Michael, should it be a basketball player or Berkeley professor? Michael Jordan, should he be a basketball player or Berkeley professor? Now these compatibility scores between a mention and an entity, we refer to them as node potentials or node features. Storing and computing them is a challenge because this requires computing similarity with as many terms as could occur in the context, and for each term you might want to learn a weight as well. So these mentions are also called lemmas and also called leaves because they generally correspond to leaves in a trie data structure. So here's an example. So after UNC workshop, Jordan gave a tutorial on non-parametric Bayesian methods. So this seems to be Michael Jordan, as in Michael Jordan from Berkeley. And how do you determine that? Well, we could look at collective signals, look at other entities in the document, but what you cannot do away with is the local contextual signals, which is the words in the context. So the contextual words are in blue here. So workshop, tutorial, non-parametric Bayesian are things that are characteristic of the statistician Michael Jordan. However, if you have to store all these features and also be able to compute their weights and use those weights at runtime in such a disambiguation model, either you need to look up a database for every word its weight, or you need infinite amount of RAM. I mean, this is not going to fit in normal memory. So on the other hand, you have some other features for Michael Jordan as in the basketball player. So these are feature vectors, and what we realize is we are trying to do a lookup. We are trying to do a lookup indexed by the lemma or the mention or the leaf of a trie, that is L. The second component is a feature itself, and the third component is the entity, the relevance of this feature in bridging the gap between this lemma and this entity. So we have these three keys in the lookup, and what we are seeking in return is the weight of this feature, the importance of this feature in bridging the relation between this lemma and this entity. So this is phenomenally large. So whether you use a collective model or a non-collective model, you need to make this lookup W, which is a function of L and E, and for each feature F. So in fact, F could be thought of as a subscript for W, as shown here. So how do you really store this efficiently? So if you use the uncompressed key value, you'll have 128 bits per entry. I mean, this is for the Wikipedia release 2 years back. So if you have even 500 million entries, 8 GB is just for this map. But then you also need to store the keys, the values, sorry. So with Java overheads, you will easily require 20 GB RAM just to store this map. So basically, we could look at alternative ways of storing. I mean, we could think of storing a map from L to F, a map from F to E, and then and the corresponding weight. Or we could think of reversing reversing the order, start from E and then go to L and then go to F. Which of them which of them is the most sensible in terms of memory footprint as well as retrieval time? So we did some analysis. We are running out of time. I'll just shed light on what we finally found useful. It makes best sense to have a map from the leaf, the lemma, to the feature, and for each feature, a candidate set of entities, This is important because not all entities get associated with all features. So Michael Jordan, the basketball player, will have probably very less to do with a workshop on non-parametric Bayesian methods. So given that sparsity, this kind of representation makes a lot of sense. So we just call it the LFEM map. And taking cues from the earlier work on efficient indexing of entities, we also make use of short entity IDs for each lemma. This is the basic same idea of using dictionaries. So what happens is you have millions of entities globally, but for a given lemma you have only a few entities. And again we use some encoding, variable length integer encoding, and also a frequent short ID as the shortest code. So we also use that heuristic. Now the next challenge was, fine, you were to store this, but is it going to be one monolithic? How many lookups? What all facilities for looking up this long array are we going to have? Because obviously we can't store the entire thing on disk and expect reasonable performance. So I'll just skip this part. So what we did is we instead of having a fragmented array of weights, we have one monolithic array of weights, which makes it easy for us to store the whole thing in RAM. But we spend some more memory on having additional lookups or sentinels, which will help us access these weights for corresponding L, F, and E efficiently. So for more information, you can look at our paper. But the point is, these are real challenges because if you want to do efficient as well as effective annotation, disambiguation, we need to look at lexical features, collective features. You need to look at models. You need to look at how you could train not only the weights for the collective model, but also weights for the individual features. So in my opinion, this area has a lot of scope for research. I will skip all this and conclude. Thank you. So there are some questions. So it looks like everyone is exhausted. So if there are none, we could conclude.
Thank you, Ganesh. Well, before we break for lunch, we have a couple of announcements coming your way. You can kindly put it up on the screen, please. Post lunch, we have all of these speakers will be speaking on the dais, so request you all to kindly do come back because we're seeing that there's a marginal decrease in the number of people post lunch, especially due to varied reasons. So we expect you all to come back because we really have a fantastic list of speakers who will be on show this afternoon. So we meet back at 1:45 post lunch. Thank you very much.